तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, we have been discussing the high electron mobility transistor based on gallium arsenide substrate. Now, the question that we have to ask is there a possibility of getting better performance in terms of mobility, in terms of higher velocities? Is it possible? In fact, if you recall, indium arsenide is one of the materials which has got very high electron mobility, low field electron mobility of about 30,000 centimeter square per volt second. So, can we make use of that? We cannot make use of indium arsenide straight away because its band gap is low, but we can mix with gallium arsenide and you can get gallium indium arsenide or indium gallium arsenide, whatever way you want to call it, you can get it and you can jack up the band gap, okay. And that material should have mobilities better than gallium arsenide. Okay. For example, I just go into this diagram, you can see this is the velocity field characteristics of indium gallium arsenide. Y is 0 is gallium arsenide. So, if you are putting gallium indium arsenide, you can put it other way also. It all depends which one you are focusing upon. I am just focusing, okay, y equals 0 is gallium arsenide. You can see the velocity field characteristic is like this, peaking around 2 into 10 to the power 7 centimeter per second, around 3 kV, or 3.2 kV per centimeter peaking is taking place. Then it saturates almost, goes down to about 10 to the power 7. If you take indium arsenide, you can see the fantastic mobility, sloping very sharply and then going right up to about 4.4 into 10 to the power 7 centimeter per second. Unfortunately, we cannot use it directly because of the low band gap. So, now you can see keep on changing y from 0 to 1, you get different curves. Other thing that I want to note here is indium arsenide will have higher mobility, higher peak velocity and everything, but it will also have a lower saturation velocity. You can see it has gone down below 0.8 right away. So, saturation velocity is smaller, but if you can operate in this region, make use of this high velocity and high velocity overshoot effects, then that is a material, but to make it useful you must have a band gap which is higher. So, take y equal to about 0.5, you can see here, that is indium 0.5, gallium 0.5, 50-50. If you take that, you can see the velocity is quite high, 2.8 into 10 to the power 7, and the saturation velocity is becoming comparable to that of gallium arsenide, tending towards gallium arsenide. So, you sort of have a mixture of the two. So, the key thing now is the lattice match between gallium arsenide and indium arsenide, or gallium arsenide and indium gallium arsenide. The whole problem is indium has a lattice constant of, or the tetrahedral radius of 1.44 angstroms, gallium is something like 1.26 angstroms. That mismatch brings in lattice mismatch. So, you are not able to grow gallium indium arsenide on gallium arsenide without defects generated, but we will see later today if possible that such a thing also is possible if you take certain things into account. Okay. We will go back to that. Right now our understanding is you need really lattice matching, you definitely need that. So, you can have a material which has a y of about 0.5 or around that. Let us go back and see now. So, that has better performance than gallium arsenide in terms of mobility, in terms of peak velocity, etc. Let us go back and see that now. Now, it so turns out that we have seen already that if you take gallium indium arsenide, where indium is 0.53, gallium is 0.47, that has a lattice match with indium phosphide. If you go back to the old curves that we have plotted, shown gallium indium arsenide lattice match with the indium phosphide. In fact, we discussed the detector where gallium indium arsenide with indium equal to 0.53 on indium phosphide. We have discussed p-ion detector like that. So, that shows that lattice match is there. So, now that means if you want to make use of gallium indium arsenide which has got better mobility, better velocity overshoot effects, etc., or better peak velocity, then you must go it on indium phosphide. So, a different device altogether based on indium phosphide substrate emerged with gallium indium arsenide as a channel material. So, gallium indium arsenide gives actually electron mobility of the order of 12,000, in fact even about 15,000 centimeter square per volt second. So, you got that much mobility which is much higher than that of gallium arsenide, and velocity, higher effective velocity is close to 3, just now we saw you get with gallium indium arsenide. Compared to gallium arsenide, it is much better. Okay. So, what you are now looking for is the gallium indium arsenide based or indium phosphide based HEMT with indium phosphide semi insulating material. On the top of that grow gallium indium arsenide. On the top of that you must put a material which is wide band gap, okay, and that material must also match with gallium indium arsenide. In fact, it so turns out that it is we will see what are those materials, aluminum indium arsenide. Okay. So, now just this is just out of interest, just to see that what sort of effective masses gallium indium arsenide has got compared to gallium arsenide. Obviously, the mobility is high, and obviously because of mobility is high, effective mass must be much lower. You can see indium arsenide has got very low effective mobility, 0.025 ratio effective mass by the actual mass, compared to about 0.7, 0.07 or 0.067 actually for gallium arsenide, it is much lower. It is just an information that I am just putting across to you that at the very x, that is x in the gallium indium arsenide, you get better and better effective masses, lower effective mass, higher mobility. That is the structure, cross section of the indium phosphide HEMT structure. Nothing new here, all that you would see is semi insulating indium phosphide substrate, buffer layer. You can grow gallium indium arsenide on semi insulating indium phosphide, lattice match is there. The buffer layer is actually grown before you actually grow the real channel material. This buffer layer, as I mentioned earlier, it absorbs any of the defects which are present in the substrate. Before you grow, if you grow the channel material on the semi insulating gallium indium phosphide, there are chances that whatever defects are present in the semi insulating substrate, impurities, defects, etc., can get absorbed by the channel layer. You do not want that. You want a buffer layer which will absorb all those defects or impurities, so that this layer is very clean. Okay. So, you can see gallium 0.47, indium 0.53 arsenic channel with quite high mobility you can get. Then this is of course what you get when you put that 2-dimensional electron gas. This is not a layer, it is actually too thick put here, it is actually a thin layer 2-dimensional electron gas, and structurally you have gallium indium arsenide on that undoped aluminum indium arsenide. Aluminum indium arsenide, you see, it is a wider band gap material compared to this gallium indium arsenide. In fact, the band gap of aluminum indium arsenide is about 1.46 electron volts, close to that of gallium arsenide. The nice thing is that layer has lattice match with this gallium indium arsenide layer. Okay. Notice here aluminum 0.48, 0.52. So, okay. And on the top of that, and this is a spacer layer which is 20 to 40 angstroms undoped, and then the doped layer must be there. if you look back the philosophy of or the principle of HEMT, an undoped lower band gap material, on the top of that a doped high band gap material separated by a spacer layer. That is the principle. You add more layers to bring in better performance, like this buffer layer, etc. So, undoped layer, lower band gap, 0.75 electron volts is band gap for gallium indium arsenide. Spacer layer undoped, 1.46 is the band gap electron volts. Doped layer, how much doping you can put, of course, now depends upon the Schottky barrier here. Okay, 1.46 electron volts band gap. Then on the top of that you see here one more material layer is added, which you call this contact layer. The whole idea is to put a layer above a wide band gap material, a lower band gap material. Okay. This can be a material which is even gallium indium arsenide, okay, which has much lower band gap. What is the idea of putting that? So that this ohmic contact is a good ohmic contact. You can make very good ohmic contact with a material which has a band gap which is low. So that is the idea. In almost all the high electron mobility transistors, you will have a top layer which is a lower band gap material. That is the contact material. Okay. You can choose your material to put which will have a good match with this particular layer. Okay. You do not care if it is a defective layer. In fact, if you want to make a ohmic contact, it will be better if it is a defective layer. Okay. When you alloy gold germanium into gallium arsenide, you have a defective layer, highly defective layer actually, alloyed contact. It makes a good contact. So that is the contact layer. So this is the structure. Now just few things about these properties of these layers, just a quick glance of these things to get a better feel, or to put a summary of the property of these materials. I put 2-3 tables. It is one table I could not accommodate in one, so split it up into several. Band gap, you can see some slight variations here and there, people quote. Band gap gallium arsenide 1.43, gallium indium arsenide 0.75, indium phosphide 1.35. In fact, aluminum indium arsenide that you put here, that also has a band gap close to gallium arsenide. Okay. You do not try to put at this stage gallium arsenide on this, because there will be lattice mismatch, but aluminum indium arsenide has got a good lattice match. So, you get a band gap material which is of that order. Okay. Indium phosphide of course 1.35. Mobility, gallium arsenide, see this 10,000 is a very optimistic value. You get, okay, it may not be exactly at that value that you get, but people have quoted these values which are some theoretical estimates. And then gallium indium arsenide about 15,000, see quite high mobility, 1.5 times that. Indium phosphide, generally people talk about 5,000, here in this particular table which I saw, it is about 6,000, maybe it is an optimistic value or some theoretical estimate. If you go, this is a pure material, how much mobility you can get depends upon how much is the purity. If you take 10 to the power 17 doping, then you can see all the mobility is rolled down. But with gallium indium arsenide, even when the doping is 10 to the power 17, you can get about 8,000. But we are not bothered about that doping, we are bothered about this undoped layer, which is the channel layer. Dielectric constant, this is important when you make this top doped layer, otherwise it is not so important. This is just as a for a completion sake I have put this all these values, because in one place you have got these materials, because these are the materials which are very popular, 13, 13.5, 12.4, not much different. L-gas also, aluminum gallium arsenide also falls into the same range. Effective mass 0.067, you can see here much smaller, indicating mobility is much higher. Indium phosphide 0.077, mobility lower than gallium arsenide. Gun threshold, the gun threshold actually is the voltage or the field at which you have the transfer from the central valley to upper valley. That is, if I have, that is the gun threshold actually is, if you have a velocity like that, that is the gun threshold. This is the field at which the electrons will be transferred from the central valley to the upper valley. So, that is called gun threshold, because people made a device called gun device, gun diode, not the gun, it is GUNN, okay, the gun diode. So, gun threshold they say, just a name that is called, is actually the electric field at which the scattering will take place from middle valley to central valley to the upper valley. Okay. That value you can see is for gallium arsenide it is about 3.2. I also see slight ranges there, but it is around 3. So, if I quote sometimes 3, just do not be taken aback by that, it is around that value 3.2. I see all sorts of values put there around that value, okay, because after all some of these things are simulated values. 2.8 for gallium indium arsenide, that is slightly lower value itself, that is for sure. If you see those curves which I have shown, just let me go back to that. See here, gallium arsenide, that is about 3.2, and indium gallium arsenide is peak is to the left, that is about 2.8. More importantly, the velocity is higher compared to the gallium arsenide. Okay. Now, this is again that EL minus ET, we used to call it as delta E there, that is the, if you have like that, that is the delta E that we are talking of, and this is the band gap corresponding to that L and tau. Okay. To distinguish between the indirect and direct, that those terms are used. So, this is the band gap that we are talking of there, it is 0.31, even there you see there are slight variations of values, 0.31, 0.55 for indium gallium arsenide, and indium phosphide I used to quote 0.55, but it is around that point, more or less same. Then mean free path and all, of course, do not worry, 0.1, and you can see that the mean free path for gallium indium arsenide is higher, which actually will give you better velocities and better mobilities. If the mean free path is smaller, scattering takes place easily, mobilities are smaller. Okay. So, now the most important parameter is the delta EC. Okay. What is the delta EC? Supposing I have, this is the aluminum indium arsenide and this is gallium indium arsenide with gallium 0.5, 0.47 here, indium 0.53, aluminum 0.48, indium 0.52. So, this is 0.47, this is 0.48, very close, but this material gives 1.46 band gap. Okay. Electron volts, and Eg2 here gives 0.75. Now, from your thumb rule, you can see what is the delta EC is. That is delta EC, and we had a thumb rule, 2/3 of this minus this into 2/3, that is approximate delta EC. Now, notice what has happened between L gas system and this. In the L gas gallium arsenide system, this band gap was 1.43 and gallium I am sorry, this was 1.9 or so, 1.93 if it is 0.4, but it was less than that. So, even if it is 1.93 and if it is 1.43, you got about 0.5, but here the difference is 0.7. Therefore, this delta EC is higher in this case. Okay. You can see that delta EC is higher is shown here 0.52. It is not exactly 2/3 of that, it is around that point, because after all the delta EC is decided by the neutral levels alignment. Let me not go back to those discussion, because we have just said that the delta EC is decided by not by chi 1 minus chi 2, but by the alignment of the neutral levels. Okay. So, aluminum gallium arsenide is a confinement layer, that is this layer if it is aluminum gallium arsenide, and if this is gallium arsenide, this is 0.3 electron volts for a particular x. You do not go to too much of x there because you are worried about aluminum contamination there. So, here this is 0.3 for L-gas gallium arsenide system, whereas if you take gallium this system, okay, if you take this particular system gallium indium arsenide and the top layer dope layer is aluminum indium arsenide, you get that delta EC is about 0.52. With indium phosphide this layer gives 0.2. I can make structure for indium phosphide and gallium indium arsenide is 0.2, just for information. These two numbers which are put here are the delta EC between aluminum indium arsenide and gallium indium arsenide. This is the delta EC between indium phosphide and gallium indium arsenide. Okay. And aluminum indium arsenide and indium phosphide, if you use that confinement layer, the top layer, and indium phosphide as the undoped layer, then you will get 0.3. So, these are numbers which one should note, in the sense this gives us further motivation to go in for gallium indium arsenide. One of the motivation is, the first one was better mobility, better velocities, peak velocities. The other thing is, because this band gap is lower than that of gallium arsenide, you can have wide band gap materials on the top and have delta EC higher. What do you gain by having higher delta EC? You get better confinement of electrons in notch. If this is higher, the quantum well is deeper, more electrons are held there, they are locked up there more. That means the maximum current that you get or the maximum transconductance that you get as a result will be higher if the delta EC is higher, particularly maximum current, because how many electrons you can hold here without opening up this, without conduction in this region. That is what is implied by that. We discussed it in the previous lecture. So, delta EC determines what sort of number of electrons and the maximum current. If you go to maximum current, then actually the signal level is high, okay, the DC current is high. So, the implication is you can make devices with low noise, signal to noise ratio high. That is one of the improvements that you get with gallium indium arsenide, with devices with aluminum indium arsenide, low noise devices, because you can go to higher currents, because the two-dimensional electron gas concentration will be higher in this case. More electrons, which is referring to your signal. Okay. Now, let us take a look at what are the different types of devices that you can make with indium phosphide based HEMT. Evidently, this is what we have just now projected: aluminum indium arsenide, gallium indium arsenide, indium phosphide, low noise application, because delta EC is large and the electron concentration is large. Another type of HEMT, I am just projecting it to you, because you have opened up real wide variety of devices that you can get when you use this type of materials. You make slight change and make changes in the arrangement, you get different performance. Depending upon your requirement, you can actually choose those type of devices. So, low noise is this one, but you will see that this type of device gives low breakdown voltage, very small compared to about 5 volts, less than 5 volts. So, when you get certain benefits, you lose in, so you may not be able to go to higher powers. So, what they did was remove this particular layer, put indium phosphide, okay, gallium indium arsenide, indium phosphide. 1.46 is the band gap there, 1.35 is the band gap there. So, you get delta EC actually slightly better, but you must be very careful here, do not blindly use the 2/3 formula. The delta EC will be decided, it will not that as high as that. Delta EC, I think you should work it out and see. The neutral level in indium phosphide is not at 2/3 below the conduction band, it is about 1/3 below the conduction band. Okay. So, neutral level here is about 1/3 below the conduction band. In fact, it is a tremendous disadvantage for making Schottky barrier on indium phosphide. See, if I take indium phosphide, you have got all those levels, conduction band, valence band. This may be 1.35, around that point. In gallium arsenide, the neutral level was here. Okay. In gallium arsenide, you have the neutral level here, EC, EV. These are all the levels, 1.43. This is gallium arsenide. This is indium phosphide. Suppose the neutral level is here, 2/3 of Eg, that is E naught. Okay. What is the barrier height that you get when you make a Schottky barrier? It is that. When the interface state density is high, the Fermi level gets locked on to that, and you get a barrier height. Okay. I will just draw that diagram here on this side. See, you get a barrier height like this. In the Schottky barrier, you get it corresponding to that. That is the Fermi level. That is 2/3. This is 5 bn. So, you are very happy with the Schottky barrier. Now, suppose that particular layer, okay, suppose you have got the band gap 1.35, and if the neutral level is here, this is E naught. That is almost Eg by 3. 1.35 and Eg by 3 is about 1.3 by 3, 1.35 by 3, that is about 0.4, 0.4, 0.45. If you make a Schottky barrier here, what will be the Schottky barrier height? Let me remove this and draw that now. Make an n-type material, so this is about roughly Eg by 3, indium phosphide. So, that is actually equal to 5 bn. What will you say about this now? This is EV, EC, EV and EF. So, the barrier height is now 0.43. It is very difficult to make Schottky barrier with indium phosphide. Okay. So, that is one of the difficulties people have faced when they made this particular thing. Okay. Only thing is you have to make modifications on the surface to improve this barrier height. So, you have to work hard to improve this barrier height. So, in fact, you will not see in literature the MESFET made with the indium phosphide. You do not see reports telling that indium phosphide MESFET. You see reports and devices fabricated with gallium arsenide MESFET, MESFETs fabricated with gallium arsenide. That is because you get high barrier height there. Here you do not get. It is not a oblique contact, but it is a very poor junction. So, if you talk of indium phosphide, you talk of a Myers field effect transition, MISFET, put an oxide layer on the top of that to make those devices. But all the same, I just put this across as another device which people think of, where system 2 is there. Indium phosphide, okay, to improve the breakdown voltage of the devices. Probably this is breakdown voltage low because of this presence of this layer which has lot of aluminum. So, they replaced it with this. If you can replace this with gallium arsenide, you are on business. Instead of replacing with indium phosphide, replace this top layer with gallium arsenide. What is the benefit? No aluminum there, band gap is 1.43, 2/3 of Pg minus 2/3 of Pg, high delta AC you will get. Whereas here 1/3 of Pg minus 2/3 of Pg. Please remember, that is why if you look at the table there, just go back to the table, see the barrier height, the delta AC is 0.2. If you go by the thumb rule, 2/3 of Eg1 minus Eg2, you will get close to this, close to 0.5, because that is 1. Aluminum arsenide is 1.46, indium phosphide is 1.35. Even though the band gaps are the same, because neutral level of indium phosphide is closer to conduction band, you get this, the delta EC with between gallium indium arsenide and indium phosphide 0.2. Please remember that. So, when you use these formulae for finding out the delta EC, do not use blindly 2/3 of Eg minus Eg1 minus Eg2. Ask yourself what is the neutral level. If the neutral level location is known, you can immediately pin it down and say how much is delta EC is. Because finally, the two neutral levels align with each other. That is the key. Okay. So, the system 2 is that we would put our money on gallium arsenide replacing aluminum arsenide rather than indium phosphide, but people have done these devices and said, look, I can get better power, medium power applications, but still the low noise is open to question, though I just put it because people have reported that type of thing. Your delta EC is 2.2, number of electrons that you can have is not as much as that. You get higher breakdown about 10 volts or something like that. No. System 3, throw away indium gallium arsenide. It is only for high power applications. That is, do not use indium gallium arsenide, keep that top layer, put this indium phosphide layer. This material has wider band gap compared to gallium indium arsenide, 1.35. Okay. Now, you can see you still get delta EC between these two, about 0.3, because it is not, see, this is 1.46 Eg, this is 1.35. If you use your formula blindly, you will get 1.46 minus 1.35, 0.1 divided by less than 0.1, but you get about 0.3. This is because the neutral level of indium phosphide is 1/3 below the conduction band. I have enough food for you to think and work out these numbers. So, now just I can run through the thing, because as a projecting these things, I have mentioned what are the merits and demerits. You know the structure now, you run through the 3 types of devices, just telling what is what. The first type, aluminum indium arsenide, gallium indium arsenide or indium phosphide is the most widely used. HEMT indium phosphide based. Here just I wanted to give you some formulae, because I wanted to correct some of the concept that we had earlier. All through what we are telling is, if you mix two materials, okay, if you mix two materials, the band gap varies linearly. It is actually not linear. In fact, I have shown you, when I shown you the X versus aluminum content in the aluminum gallium arsenide, it is not linear, it is slightly non-linear. This is actually the equation that was given, it is reported in literature. Eg is 0.356 for this system, aluminum indium arsenide, 0.356 plus 2.35 into Y, where Y is aluminum content. Yes. So, that is about 1.46, where Y is equal to 0.48. Okay. It is 1.46, 1 Y is there. That is how you get, because if you try to put it linear, you will not get it. The same case is true with the gallium indium arsenide. Gallium indium arsenide, it is not exactly linear as with X, though we had plotted approximate curve fitting into that thing and said, but then you will not get at X equal to, if you put linear at X equal to 0.47, you will not get 0.75. In fact, I had one of our friends here reporting that that formula does not fit in. It is true, it will not fit in. The correct thing is this. Okay. So, 0.75 because of the slight non-linearity. This is just for completion's sake. Okay. Now, you can see between these two systems delta H is 0.71 and delta H is 0.52, close to the 2/3, because this is E naught is at 2/3, this E naught is at almost at 2/3. That is, you get that. That is what it gives you better confinement of electrons, more number of electrons in the notch. This is just reproduction of this diagram which you have drawn right at the beginning, because at the end of the those example numbers, this is the structure: indium phosphide, buffer layer, gallium indium arsenide, this layer, this layer. Now, this buffer layer can be gallium indium arsenide, or it can also be aluminum indium arsenide, or if you want to hear one more jargon, superlattice structure. What is superlattice structure? It is alternating wide band gap, small band gap, wide band gap, small band gap material. See, some of these terms must be familiar. These are coined as and when. See, if I have a material these are very thin layers, 5 angstroms, 10 angstroms, each one of them of that order, or maybe 20 angstroms, thin layers of wider band gap, that is EC, that is EV. This type of structures are called superlattice, where you have wide band gap, narrow band gap, wide band, narrow band gap. It is just like, if you have atoms. I have no explanation seen in the literature saying why you call superlattice, but it is very clear. If you have atoms nearby, in the lattice, what do you have what is the potential variation? If you take atom, when you move from one atom to another atom, you have got that superlattice. You have got the potential variation. As you go near the atom, there is a dip in the potential. Okay? You have got the potential variations going like that. You have got the potential variation going like that. It is like in the case of lattice, you have got the spacing between lattice atoms which are few angstroms. Same way, if you keep these layers very thin, it is equivalent of the lattice atoms. That is why called this as superlattice. Wide band gap, narrow band gap, wide band gap, narrow band gap. How many number you want is your choice. You may have 10 angstroms, 10 layers you put like that, you get 100 angstroms. In fact, this layer should be as thick as possible. This is a buffer layer which absorbs all the defects from here, at least 0.8 microns layer. So, if you want superlattice, it is very easy to grow in the case of MBE. How do you grow that? Switch from L gas to gas, L gas to gas. Gas means not gas, gallium arsenide. You have got aluminum gallium arsenide, aluminum gallium arsenide, gallium arsenide. So, you have got the arsenic source all the time open, okay, and have the gallium source also all the time open. You move from here, you have gallium aluminum source also put, either MOCVD, aluminum, no aluminum, aluminum, no aluminum. Gallium and arsenic is all the time present. It is that type of structure. I just deliberately brought into you because do not be flabbergasted if somebody comes out and I use the superlattice. It is nothing but a heterostructure, number of heterostructures which are present there. Okay, so that is the most interesting part of that particular thing. So, this is a layer which is just protecting this channel layer from the contaminants, defects, etc., present in the lower layer. Now, these are some of the performances. L gas indium phosphide system, that is what your system 1. 0.2 micron gate length HEMT devices with gallium indium arsenide. This is what I am trying to point out. People have done this device, they have fabricated with this buffer layer made up of gallium indium arsenide or aluminum gallium arsenide. They found that this is much better, probably because if you put aluminum indium arsenide, that adds itself source of defects because of aluminum presence. So, that may be the cause, I can say. So, that is what is said here. This layer gathers, that is, shows better results than with the aluminum arsenide buffer. That is, you use gallium indium arsenide buffer than aluminum indium arsenide. Okay. Apparently, the superlattices have given better performance, but it is harder to grow because you have to switch from one layer to another layer within that structure. Buffer layer should be sufficiently thick, that particular layer between the semi insulating layer and the channel layer, okay, to with low, and it has no doping. That is why I drawn this like this. If I have doping, there will be bending in these things. There is no bending here, just potential wells put in between, that is all. You will have an average band gap corresponding to that. If you have this like this, you can talk of a band gap corresponding to that on an average. That is the trick that they do with there. You can create wider band gap material depending upon the thicknesses of those lattices, superlattices. Transistor performance, maximum output conductance of course is this output, the slope it indicates. More than that, what we have to look at is effective velocity is 3 × 10⁷ and mobility of 12,000. Cutoff frequency 175 gigahertz, that is really fantastic. And transconductance with 0.1 micron gate length. See, you should be careful of course here that what sort of channel lengths you are using. I do not have both things together, 0.1 micron indium phosphide based device, 0.1 micron gallium arsenide based device. Okay. But for this it gives about 1000 millisiemens per millimeter, whereas what we saw in the previous lecture for gallium arsenide for a 1 micron device is about 400 at 77 degrees Kelvin and room temperature about 225 millisiemens. So, all that we are telling is this gives very good performance. Comparative statement I do not find, because the people working on the indium phosphide shout from the rooftop the indium phosphide is a material, but people working on gallium arsenide say that they will project gallium arsenide based device. In fact, ultimately I would think gallium arsenide based device has a better say in various aspects, because that is a better known technology, cheaper than indium phosphide, but easy to handle all those. On the same count of course, silicon guy will say silicon is the best material, but you cannot get this sort of performance with silicon. And of course, as I mentioned earlier, this cell gas indium phosphide system has low noise performance because of the higher sheet densities in the 2-dimensional electron gas. Higher sheet density because electron concentration is high, because delta EC is higher. So, this is the aspect that one has to remember. So, that is where you must see where it can be used. Do not use just wherever you like, you can use it in those applications, but you cannot go to higher voltages, 5 volts upper limit. So, low voltages, low noise etc., you can use that. System 2, but let us quickly go through that. System 2 is instead of aluminum indium arsenide, you put indium phosphide. Okay. It is not flourished so much, but people have projected it, tried various things. It gives, because this layer, the first type aluminum indium arsenide or gallium indium arsenide gives breakdown voltage less than 5 volts. They said let us try putting indium phosphide in that place, because this is containing a lot of aluminum. This overcomes the above problem, you get about 10 volts or so. But the main problem with the indium phosphide is system 2. Please remember, system 1 and system 2 difference is the top layer instead of aluminum indium arsenide, you put indium phosphide. But the moment you put that, it has problem, low Schottky barrier rate. Just now we explained that. So, what they did is they put on the top of that 150 angstroms of it. This is just various, the moment there is problem, there are people to play games on that, try all sorts of tricks to overcome the problem. They put gallium indium phosphide with 18% gallium, which gave barrier rate of 0.64, better than 0.4. Okay, you get a Schottky barrier. There is on the indium phosphide layer, put gallium indium phosphide layer, which has lattice match. System 3. Obviously, we are running through the thing, because after all we understand what is required, and aluminum indium arsenide or gallium indium arsenide is the most popular device in indium phosphide based, but people have been taking a look at other materials. System 3 is the top layer keep as aluminum indium arsenide, replace the gallium indium arsenide layer by indium phosphide to improve the breakdown voltage. That will give you definitely better, because indium phosphide is a wide band gap material compared to gallium indium arsenide. Okay. You still get, I think, the delta EC of about 0.3, because it is not two-thirds. The neutral level is at 1/3 below the conduction band. Please understand that. Delta EC is 0.35 to 0.4, not exactly 0.3. Okay. This is the cross section of that particular device. Same device, semi insulating layer, buffer layer indium phosphide, undoped indium phosphide layer, there is a channel, undoped aluminum indium arsenide, aluminum indium arsenide. All that you have done is, instead of indium gallium arsenide, you put indium phosphide. People expect this to give better performance than gallium arsenide because of high velocity overshoot effects. Devices with now you can see the comparison is not existing, 0.3 micron device, gate length, GM 610 millisiemens per millimeter, quite good. FT 76 gigahertz, not as good as indium gallium arsenide. That was 750 gigahertz, but 0.1 micron channel length. So you can see the comparison not there. Maximum frequency of operation with that for unity power gain, that is the F max, is power gain unity 140 gigahertz. Disadvantage, indium phosphide, the mobility is low compared to gallium arsenide and gallium indium arsenide. It is about 5,000, okay, when it is pure material. So much lower, low on resistance because of that, high on resistance, I am sorry, high on resistance because of that. That is the disadvantage. You have to pay for everything. You want higher breakdown voltage, and you pay by putting this one, but there are better devices. Now let us just take a look at one more thing. In the gallium arsenide based, I am just leaving the indium phosphide based system right now. Go back to the gallium arsenide based system, where they have, after seeing all these things, the gallium arsenide guy started getting worried, okay, because that is a better technology. What better performance, what you do? If you recall yesterday what we said, okay, the problem was, see, this is the gallium arsenide based HEMT. We discussed now indium phosphide based systems. There are 3 types, out of which aluminum indium arsenide, gallium indium arsenide based or indium phosphide is best. You get high performance. Now going back to gallium arsenide based, semi insulating gallium arsenide, buffer layer 0.8 micron, it can be again superlattice or undoped gallium arsenide, 0.8 micron undoped gallium arsenide, okay. This thickness can be reduced, there is no need of 0.8. Then 30 angstroms of undoped aluminum arsenide, gallium arsenide. Now this is the same as what we have been discussing. Just to avoid confusion, that I am putting it here. So you have the undoped gallium arsenide on semi insulating gallium arsenide with a buffer layer, of course, in between. I am just skipping that to avoid confusion. This is a channel layer, and on the top of that you have a spacer. What is that? Undoped L gas. On the top of that you have got usually doped L gas, and then of course you have the Schottky barrier, and you have the contacts here, source, drain. Okay. Now we saw the problem with this device was, forget about that one aluminum content, but you are putting up with that because you get about 0.3 delta EC and good device. To get better transconductance, what you have seen is you have to reduce the thickness of this layer. You must reduce it, but when you reduce the thickness, what happens? You get better transconductance, but then you must increase the doping. When you increase the doping, upper limit comes up because of this Schottky. So what you do is, if you look at the diagram, you will choose this as 10^15 top layer, but you introduce a layer which is very thin. Introduce a layer which is very thin, of the order of about 3 angstroms, that is the delta doped or the planar doped. This layer is 8 into 10 to the power of 18 per centimeter cube. Notice what is required is the total integrated doping here. Put very heavy doping here, just near the spacer layer, which will supply all the electrons which are required here. That is the channel. And this layer which is making contact with this Schottky, make it lightly doped. So, total integrated doping is here is high. This type of device is called delta doped or pulse doped or planar doped. Okay. So, you call it as delta doped or delta doped pulse doped or planar doped. Any one of the names, okay. So, if you hear the delta doped HEMT, do not get worried. It is the same drink in a different cup. Okay. So, same old wine in the, so that is the thing, that is proud. Only difference is you have put heavy doping here close to that, just few 3 angstroms. Now, you can understand the extent of pressure the technologist bears. He has to grow at 10 to the power of 18 into 8 into 10 to the power 18 doping layer, which is about 3 angstroms layer, that control over the entire layer. So, that is the pressure is taken by the technologist ultimately. Okay. So, this is it. Here also you can see there is a contact layer, which is actually a smaller band gap material. So, benefit of this pulse doped HEMT is higher breakdown voltage, okay. Higher breakdown voltage because gallium arsenide substrate is there, okay, and you do not change aluminum content too high, it is 0.26. Higher 2-dimensional electron gas, more doping is there at the edge, more electrons will be collected here. Okay. So, because of that you get higher 2-dimensional electrons at the edge density, because that band bending will depend upon how much is the relative doping between the 2 layers is PBI plus delta EC. PBI goes up if the doping is higher. Higher intrinsic transconductance, why? You can now afford to reduce the thickness, because all the doping is present here. You can reduce the thickness. Once you reduce the thickness, the CS is actually larger, higher transconductance you get. Better control of threshold voltage. Without worrying about doping, you can change the thickness. So, you get better control of it. That is the doping concentration, total doping concentration is at Vp0. So, you can get better control without worrying about thickness. And of course, linearity of the transconductance also just an added merit, but I think these are the main advantages here. I will not touch upon much on this now, but I will just show you, because I have just few minutes left out here. There is another type of device which has emerged over the past few years. I am taking right up to the current now. The another type of device which is emerging, where you can use gallium indium arsenide as that channel layer with gallium arsenide substrate. Nothing like that, because today you can get semi insulating gallium arsenide which is very pure. You do not have to worry about the buffer layer, you do not have to worry about defects migrating, but still you can put a buffer layer and you can put gallium indium arsenide on gallium arsenide. Now, what are you worried about? I will take up detailed discussion next time, but I will just tell you what is going to be the thing here. You are worried about realizing a epitaxial layer of gallium indium arsenide on gallium arsenide, because lattice mismatch. What happens if there is lattice mismatch? If you can tolerate that lattice mismatch, if there are no defects generated during that growth, then you can put gallium indium arsenide on gallium arsenide. So, gallium indium arsenide channel layer which will give high mobility. On the top of that put gallium arsenide, which is the N plus layer, which actually you can make it also the delta doped, then you do not have the problem of the aluminum content. You have got 1.43 is the band gap of gallium arsenide, you have got gallium arsenide band gap is 0.75. So, you got 0.5 electron volts as the delta EC. So, that sort of thing you get, benefit you get. So, there if you see, I will go through this particular detail the next time, but this is the substrate of one lattice, this is substrate of another lattice constant, this is more. If you arrange, you can get this type of structure where the intermediate layer is defective, you can see the bonds are broken. That is what you get. If you grow lattice mismatch devices, tremendous amount of stress is there, pulling each other and defect will be generated. What we would like to show is or see is that you can generate without defects a layer like this, provided you grow a very thin layer. That is called a strained layer concept. We will discuss that in the next lecture. Few things before we go to HPT.